In our energy skate park lab, y'all saw that skaters' potential energy turn into kinetic energy at the end. We're doing that today, but with we're analyzing it with using math. So we're going to figure out this 600 kilogram boulder's potential energy, because it's its mass and its height, and we can do that with that. And then we're going to figure out if it fell. This is also like what we did in your other lab. If it fell, how fast would it go? So let's check it out. So our mass of this boulder is 600 Ks. It hung from a rope 5 meters above. That's our height. And remember, your height is always negative because that thing has the potential to fall down that distance. We're on Earth because it's got a coyote right there, and coyotes are on Earth. And it's asking how fast. So we can't go straight to how fast. First we have to figure out its potential energy. So we're going to, oh my goodness, we're going to use MGH, and then plug everything in. Let's see, M is 600, G is negative 9.81, and H is negative 5. And when I multiply all those, my calculator gives me 29430 joules. So here's where we're switching to kinetic energy. So it's going to convert all this energy into kinetic energy. So if I were to throw this thing up, I know y'all can't see past here virtually, but if I throw this thing up in the air, it stops and then it comes back down. See? At its highest height, this amount of potential energy it has is the same amount of kinetic energy it'll have right before it hits the ground. Because it's not moving up here, it has zero kinetic energy, it's all potential energy. Here it has a little bit of height and some kinetic energy. It is accelerated for this far, but after it gets way down, boom, right before it hits the ground, it's going really fast. And it has nowhere left to fall, so it has zero potential energy. And all of this, if this were the boulder at the 5 meters, all of this 29430 joules turns into kinetic energy at the end. So instead of zero kinetic energy and 29430 potential energy, at the end it has zero potential energy, and it's that 29430 is all kinetic energy. So I'm going to, let's see. We can use this 29430, that was our potential energy, but it all gets turned into kinetic energy. And we're about to try to find V. It's asking how fast. We're looking for V. It's still the same old boulder, so the mass is still 600, doesn't change. And that's all we need. So alright. There's our formula. I gotta plug in my 29430 for my KEs. Is that how you draw 9? 29430. Mass is 600. We're looking for V. Ah, my green marker's dying. Look at that. So now we can simplify. 1/2 times 600 is 300. That's V squared. Remember, don't forget your squared. That's the hardest part of this one, is remembering that squared. It says V squared times 300, and I wanted to get it to say V squared and then just V. So V squared times 300, I want to make that 300 cancel just to get to V squared, so I'll divide both sides by 300, doing the opposite. I apologize for my squeaky marker. 29430 divided by 300 is 98.1 probably. That's V squared. We need to get to V. So square root of V squared is V, and square root of 98.1, remember your math teacher would say that that's plus or minus 9.9 is what it turns out. So we know that this thing is falling in the down direction. It was up high, and now it's falling down. So it may be plus or minus 9, but we know which one it actually is. It's negative 9.9 because we know it's falling down. Oh. And there we go. There's some questions on your assignment that will ask you for potential energy and then say, okay, well, how fast will it go? And then towards the end of it, it starts doing what this one did, and just saying, it has this mass at this height, how fast will it go when it falls? And you have to figure out potential energy, and then take that potential energy and plug it in for kinetic energy, since it all gets converted by the time it is about to hit the ground, and then figure out how fast it's going at that point. Does that seem all right? Please try this out. The P to KE convergence.